In this lab, we will be looking at electricity and the components associated with electricity, such as voltage, resistors, current, and all the various physics formulas that we can apply to solving these problems. So that yes, we know what electricity is, but do we really know what it is, where it came from? Can we see it? Do we know how it was created? Electricity is the force that's created by differences in charges due to a loss or gain of electrons. Remember, electrons have a negative charge. So that when electrons flow between 2 points, this is actually electrons moving from point A to point B, and this is what we call electric current. In order for the electrons to flow, there must be a difference in the charges or the number of electrons that's built up between the 2 points. Just like heat flow needs a difference in temperature, electricity always flows from a location with a negative charge to a location with a positive charge, because like charges repel and opposite charges attract. Think of a battery. The top has a positive charge and the bottom has a negative charge, so that when they are connected, electrons flow from the bottom to the top. So that electricity, as it moves, we're looking at the flow of electrons from one place to another. This is measured in amperes, abbreviated amps. So the amp is the amount of current flowing past a given area per second. Electric current is the flow of an electric charge from one place to another. So it's defined as I, and the unit is coulombs per second. And we have our formula right here where we have our electric current equaling our change in our charges over time. So a closed path through which a charge can flow and return to its starting point is called an electric circuit. Current is defined as the rate at which a charge flows through a surface. So we have our formula that we want you to write down for our current. The current is in the same direction as the flow of positive charges, and again, the I is going to stand here for the intensity. If we look at an example, a battery uses a chemical reaction to produce a potential difference between its terminals. It causes the current to flow through the flashlight bulb, similar to the way the person lifting the water causes the water to flow through a paddle wheel. If a battery is disconnected from any circuit, it has an electric potential difference between its terminals. This is called electromotive force, or EMF. The symbol can be written as EMF or as a capital E. Remember that even though its name is EMF, it's an electric potential, not a force. The amount of work it takes to move a charge, Q, from one terminal to another is work would equal our charge, or our change in charge, times our electromotive force, or EMF. Looking at potential difference equals voltage, which equals EMF. In a battery, a series of chemical reactions occurs in which the electrons are transferred from one terminal to another, and so there will be a potential difference, or a voltage, between the poles. The maximum potential difference that the power source can have is called the EMF, so that our voltage equals our potential difference, which equals our EMF. The direction of current flow from the positive terminal to the negative one was decided before it was realized that electrons are negatively charged. Therefore, current flows around a circuit in the direction a positive charge would move. Electrons move the other way. This does not matter in most of our circuits. Finally, the actual motion of the electrons along a wire is quite slow. The electrons spend most of their time bouncing around randomly and have only a small velocity component as opposed to the direction of the current. The electrical signal propagates much more quickly. Drift velocity, when we look at the free electrons that move in the direction of acceleration with an average velocity, we call this drift velocity. Remember, the direction of the current is the direction that the positive charge would flow, and this is called conventional current direction. It is common to refer to a moving charge as a mobile charge or a mobile charge carrier. The electric current, we can have electrons that move through a metal wire. The symbol for electric current will be I. If we look at the relationship between current and drift speed, charged particles will move through a conductor at a cross-sectional area, and we're going to call that area A. N is the number of charged carriers per unit. So N times A times change in X is the total number of charged carriers. Going back over this, the total charge is the number of carriers times the charge per carrier. Change in Q would equal N times A times change in X, all of that times Q. The drift speed will be VD for velocity of drift, is the speed at which the carrier moves, and that'll equal the change in X divided by the change in time. And then we can rewrite all of that and sub all of those components in, so that if we're looking here, we can sub in for Q, we can sub in for time, and then we've got our formula that we have here. If the conductor is isolated, the electrons will undergo random motion. And so when an electrical field is set up in the conductor, it creates an electrical force on the electrons. Therefore, it creates a current. The drift speed is much smaller than the average speed between collisions. When a circuit is completed, the electric field travels with a speed close to the speed of light. Although the drift speed is on the order of 10 to 4 meters per second, the effect of the electric field is felt on the order of 108 meters per second. The source that maintains the current is a closed circuit, and it's called EMF. So any device that increases the potential energy of a charge circulating in the circuit would have this. For example, batteries and generators. Remember that the units are volts and that EMF is the work done per unit charge.